The Great Wall of China and the Taj Mahal have been joined by another wonder of the world in the Delta region of Holland. In the latest in our series of features called Floating Future from the Lowlands of Europe, we introduce you to a huge flood barrier known as the Maaslandkering. The structure is the last line of defense for the port city of Rotterdam.
After Rotterdam's old-style brick buildings were destroyed in the Second World War by German bombing, the city became a playground for modern architects. These cubist residential blocks based on tree houses are a forest of 51 homes, along with the Pencil building and the central library with pipes outside. The architecture in Rotterdam is like a Legoland for adults. On the same river that reflects modern buildings is an historic boat. The mixture of old and new is right here at Rotterdam's waterfront. Rotterdam is not even the largest city in Holland, but for many years was the biggest port in the world. It used to handle 500 million tons of cargo a year. In 2004, it was overtaken by Shanghai, but even today, on average, one ship comes in or out of the harbour every 6 minutes. Yet the biggest port in Europe and Holland's second largest city is an average of 2 meters below sea level. So how is Rotterdam protected from river and sea flooding?
We talk about approximately 100 billion euros that is necessary for this plan. This was accepted as part of our issues in living in the lowland, in the delta land.
The Delta Plan is the most ambitious sea defence network in the world. The most impressive part of the project is the Maasland Barrier, or Maaslandkering, which was completed in 1997. To span the 360-metre wide river, 2 huge doors were built, each higher than the Eiffel Tower.
So the site that we're standing on right now is actually 2 meters above sea level. Now when we have closing procedures, the water will come to 3 meters above sea level, and it will around be the top of these gates.
In the event of a 3-metre high flood or storm surge, a fully automated decision and support system will be activated to avoid human error.
So from this side the water will come. This is seaside, this is riverside.
The decision to close the massive steel doors is controlled by a computer system. The water pressure the barrier must sustain is around 35,000 tonnes. An 80-centimetre gap is left between the doors to stop them banging together and damaging each other. Of course, all the pressure is then transferred to the ball joints on either bank.
Now we're standing here at the ball joint, and the ball joint is really important to us because the ball joint is actually the whole turning point of the barrier. So let's say we're actually here and the barrier goes like this.
The 10-metre diameter ball joints and sockets were made to an accuracy of 2 millimetres. So how does the door keep turning under pressure?
Now when the force of the doors of the water comes onto this joint, that's when it's pushed back into the polyethylene, and under this enormous pressure the polyethylene will completely melt. And that way it will lubricate the ball joints.
Every time the barrier is closed, the ball joints are pushed back 20 centimetres into lubricating polyethylene pads, which must be replaced after being used 5 times. They're designed to withstand a force of 70,000 tonnes.
So we're protected up to 5 meters above sea level. Now, water levels up to 5 meters above sea level, that's really high levels we expect to happen only once every 10,000 years.
The 22-metre high gates are floated into position, then the 15 chambers inside the doors, apart from the chamber that houses electronic equipment, are flooded to stabilise the barrier. The water on the riverside is about 17 metres deep. The difference of 5 metres is the limit. There is also major construction work under the water. To stop the riverbed washing away beneath the barrier, 4 layers from fine to coarse materials were installed. Finally, a sill of 64 concrete blocks, each weighing 630 tonnes, was laid on the riverbed. Even on a still and calm day, these steel girders, which are 1.8 metres in diameter and 9 centimetres thick, can be tested by the elements.
Now as you can see, it's white, and it's white for a special reason, because there's a coating on it, and the coating will protect the whole steel construction Not only from corrosion, but also from expanding or shrinking too much.
Fine engineering on a massive scale, Rotterdam's final line of defence is an impressive structure. Whether it can pass the test of rising sea levels is another question.
In the low-lying nation of Holland, to reclaim land from the ocean, a whole inland area of sea was turned into a freshwater lake. Complex systems of sluice gates were later installed to balance the water levels on either side of the dikes. But however impressive the hydro-engineering products in the Netherlands, they may not be able to pass the test of global warming and rising sea levels. In the latest of our series of reports called Floating Future, we look back at the past and forward to the future of sea barriers in Holland.
The level from this, that is nothing. This is the same every day.
It's the same every day.
And this is high and low.
Also that changes for the fresh water.
74-year-old retired engineer R.E. Vig now proudly shows visitors around the Haringvliet sluices, which took 14 years to complete.
It's the biggest lock from the world. And that I tell to the American too. Dit are the biggest lock from the world.
This world record holder plays an important daily role for Holland. The barrier has 17 sluice gates, separating salts from fresh water. The sea level is usually above the level of the river, so when the tide falls, the 10.5-metre gates are opened to allow the fresh water to flow into the sea. The gate moves at a rate of 1 centimetre per second, so it takes 20 minutes to be completely opened or shut. Of course, at high tide, the gates must be closed to stop seawater intrusion.
You can see the black one. And this going in, and then is coming up the door on this triangle.
The control mechanism for the sluice gates is hidden in this cavernous triangular concrete tunnel.
When it's coming in, the door is closed. When it's coming out, the door is open. And over there you can see is over 7 meter now, and it's going 5 meter more.
The concrete tunnel takes us back through the passage of time. Half a century ago, you can see a 1 kilometre long dike sitting in the middle of the estuary. A temporary harbour was built, and the construction site, which had to be constantly pumped dry, even had its own power station. There were 22,000 concrete piles alone, not to mention 3-metre square concrete blocks that were used to fill in the sea. So a specialist concrete factory was also built. 22 triangular units in the shape of Greek harps were placed side by side and linked together with steel cables. The completed floodgates, locks and road bridge span what you could say is the most important estuary in Western Europe. Over 60% of fresh water from the Rhine and Maas rivers is held back or let through the 17 sluice gates. To protect the Haringvliet from ice in winter, closer inspection reveals sloping knives disappearing into the water below the riverside gates.
As ice is coming, that is a security for the doors. They're breaking the ice.
There are a dozen or so barriers and sluice systems along the southwest coast of Holland in the Delta Works project. But the one the Dutch say was the first to keep out the sea is this huge dike in the north of the country.
This where we're here staying is the IJsselmeer. It used to be the Zuiderzee till 1932. Then it was closed by the dike.
The Dijk blocked off a large inlet of the North Sea, called the Zuiderzee, and turned it into the freshwater Lake IJssel, or IJsselmeer. The 30-kilometre barrier cut off 300 kilometres of coastline and created 220,000 acres of new land. Traffic passes along the line between lake and sea, or more accurately, along the artificial division. You can clearly see the water level at the IJsselmeer is below that of the sea. The Dijk may soon be put to the test by global warming.
30% van de dijken zijn te laag. En tenslotte is het zo dat met een vooruitziende blik we deze zaken nu hebben aangepakt en we niet wachten op een ramp.
To avoid being taken by surprise, the Netherlands has to throw at least €1 billion into the sea every year.
The traditional engineering solution to this is to build higher dikes to protect, but of course this becomes very expensive. If you have to build them very high, you can also use other kinds of solutions like wetlands, coastal wetlands, salt marshes and things like that that can help absorb the impact.
The choice between engineering projects that reclaim land from the sea or ecological management of rivers and coasts is a tug of war between security for today and sustainable development for tomorrow, which may continue for some time to come.